Hello everyone. Welcome back to my course Aerospace Engineering, Basics of Aviation Engines. In this video, we will talk about turbojet engines. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Jet engine fundamentals. A jet engine is a type of reaction engine, meaning it produces propulsion by expelling a mass in one direction in order to move in the opposite direction. This principle is explained by Newton's third law of motion, which states that for every action or force, there is an equal and opposite reaction. In the case of a jet engine, the action is the high-speed exhaust gases being pushed out of the engine. The reaction is the forward thrust that propels the aircraft. Most jet engines used in aviation today are air-breathing gas turbine engines with an axial flow design. Being air-breathing means the engine uses oxygen from the surrounding atmosphere rather than carrying its own oxidizer. The term gas turbine refers to the method by which energy is extracted from hot combustion gases using rotating turbine blades, which convert thermal energy into mechanical power. The operating cycle of a jet engine begins at the engine intake, where ambient air from the atmosphere is drawn into the engine. This incoming air is directed toward a compressor, which may be axial, centrifugal, or a combination of both. The purpose of the compressor is to increase the pressure and temperature of the air. Compressing the air is essential because high pressure, high temperature air allows for more efficient and stable combustion later in the process. As the compressor rotates, it progressively squeezes the air as it moves through multiple stages. By the time the air exits the compressor, it has significantly higher energy content compared to the air entering the engine. After compression, the high-pressure air enters the combustion chamber. In this section of the engine, fuel is sprayed into the hot, compressed air and ignited. Once ignition occurs, the combustion process becomes self-sustaining. This is because the continuous flow of air from the compressor and fuel from the fuel system maintains a steady flame within the combustion chamber. The burning fuel-air mixture produces extremely hot, high-energy gases. These gases expand rapidly, increasing their velocity as they move toward the rear of the engine. The energy contained in this exhaust flow is what ultimately powers both the engine components and the aircraft itself. The hot exhaust gases leaving the combustion chamber pass through one or more turbine stages. These turbines are connected to the compressor by a shaft, and as the gases flow over the turbine blades, they cause the turbines to rotate. This rotation provides the mechanical power needed to drive the compressor, allowing the engine to continue operating continuously. Although the turbines extract a significant amount of energy from the exhaust gases, not all of the energy is used. The remaining energy stays in the exhaust stream, which is still moving at very high speed and temperature. After passing through the turbines, the remaining exhaust gases are expelled through a nozzle at the rear of the engine. The nozzle accelerates the exhaust gases to a high velocity before releasing them into the atmosphere. This rapid expulsion of mass in the rearward direction creates a forward thrust force, which propels the aircraft. A turbojet engine is most efficient when the speed of the aircraft closely matches the speed of the exhaust gases leaving the engine. Under these conditions, the engine converts fuel energy into thrust with minimal losses. In many practical situations, aircraft operate at speeds that are much lower than the exhaust velocity of a pure turbojet engine. To improve efficiency under these conditions, engine designers use the turbine section to drive additional components such as fans, propellers, or other mechanical systems. By doing this, more of the engine's energy is converted into useful thrust at lower aircraft speeds. This design approach leads to different types of gas turbine engines. Turboprop engines use turbine power to drive a propeller, making them well suited for slower aircraft and short-haul operations. Turbofan engines use a large fan to move a greater mass of air at a lower velocity, improving efficiency and reducing noise for subsonic transport aircraft. Turboshaft engines primarily deliver shaft power rather than direct thrust and are commonly used in helicopters. Each of these engine types is optimized to match the speed and operational requirements of the aircraft it powers. Turbojet engine. A turbojet engine is a type of jet engine that produces all of its thrust by accelerating and ejecting a high-energy stream of exhaust gases through the engine's exhaust nozzle. The forward motion of the aircraft is achieved entirely through this high-velocity exhaust, which creates thrust according to Newton's third law of motion. There are no additional systems, such as large external fans or propellers, contributing to thrust production in a pure turbojet design. One defining characteristic of the turbojet engine is that all of the air entering the engine intake passes directly through the engine core. This core includes the compressor, combustion chamber, and turbine stages. Unlike turbofan or bypass engines, there is no portion of the incoming airflow that bypasses the core to produce additional thrust. As a result, 100% of the intake air is compressed, mixed with fuel, burned, and expanded through the turbine and exhaust nozzle. Because all thrust is generated by the high-speed exhaust gases, turbojet engines produce very high exhaust velocities. This makes them well suited for high-speed and high-altitude flight, where the aircraft speed more closely matches the exhaust speed and efficiency improves. However, at lower speeds, this same characteristic leads to lower efficiency, higher fuel consumption, and increased noise when compared to turbofan engines. The simplicity of the turbojet design makes it mechanically straightforward, but its operational limitations have led to its replacement by more efficient engine types in most modern commercial aircraft. Today, turbojet engines are primarily found in military aircraft, experimental aircraft, and early generations of jet-powered designs where high speed and compact engine size are critical. Main features. Turbojet engines are commonly found in military fighter jet aircraft. These aircraft are designed for very high speeds and rapid response, which makes the turbojet engine well suited for their operational requirements. Fighter jets powered by turbojet engines are capable of flying at extremely high velocities, but this performance comes with certain trade-offs. They are typically very loud and have a relatively limited range compared to aircraft using more fuel-efficient engine types. One of the most important characteristics of a turbojet engine is its excellent thrust-to-weight ratio. The engine is capable of producing a large amount of thrust relative to its size and mass, which is critical for military aircraft that require fast acceleration, high climb rates, and agile maneuvering. The compact design of the turbojet engine further supports these performance demands by allowing it to be installed in airframes where space and weight are limited. Turbojet engines are commonly equipped with a built-in starter generator system. This integrated component allows the engine to be started and to generate electrical power once it is running. Electric starting systems are widely used, simplifying engine start procedures and reducing the need for complex external equipment. Another advantage of the turbojet engine is its ability to restart both on the ground and in flight. The starting sequence is typically short, allowing the engine to reach operating speed quickly. In certain conditions, the engine can also be started using windmilling, where airflow through the engine causes the compressor and turbine to rotate without external power. This windmill starting capability can occur in a very short time frame. Turbojet engines may also be designed with specialized features such as saltwater recovery capability, which is important for military operations involving overwater missions. Additionally, manufacturers often allow customer-specific modifications, so the engine can be adapted to particular operational needs or aircraft designs. Despite being optimized for high-speed performance, some turbojet engines are designed to achieve relatively low fuel consumption for their size and thrust class. They are also capable of producing high levels of electrical power, which is essential for modern military aircraft systems, avionics, and onboard equipment. Main components of a turbojet engine. A turbojet engine is made up of several major sections that work together to produce thrust. These sections include the inlet and the gas turbine engine itself. The gas turbine engine consists of the compressor, the combustion chamber, the turbine, and the exhaust nozzle. Each of these components has a specific function in the overall operation of the engine. The inlet and its role. The inlet is listed separately from the engine because it is considered a part of the aircraft rather than a part of the engine. Its primary purpose is to capture ambient air and deliver it smoothly and efficiently to the engine compressor. The inlet is designed to provide the compressor with a steady airflow at the correct pressure and velocity, regardless of the aircraft's speed or flight condition. Because the inlet is integrated into the aircraft structure, its shape and design depend heavily on the aircraft's mission and performance requirements. High-speed aircraft, such as fighter jets, use specially shaped inlets to slow down and condition the incoming air before it enters the engine. Although the inlet does not produce thrust or mechanical power, its performance has a direct impact on engine efficiency and reliability. The gas turbine engine core. The gas turbine engine begins with the compressor, which draws in the air delivered by the inlet and increases its pressure and temperature. This compressed air is then directed into the combustion chamber. Inside the combustion chamber, fuel is introduced into the compressed air and ignited, creating a continuous and controlled combustion process. The result is a flow of high-energy gases with greatly increased temperature and velocity. These hot gases flow next into the turbine section. The turbine extracts a portion of the energy from the gas stream to drive the compressor through a connecting shaft. This energy transfer allows the engine to operate continuously once it has started. Finally, the remaining exhaust gases pass through the exhaust nozzle. The nozzle accelerates the gases and directs them out of the engine at high speed. This high-velocity exhaust produces the thrust that propels the aircraft forward. Example of a military jet engine, Pratt & Whitney F100. The image shown is of a Pratt & Whitney F100 jet engine, which is used in the F-15 and F-16 fighter aircraft. From this image, it is clear that jet engines are highly complex and precisely engineered machines made up of many interconnected components. The image of the F100 engine does not include the aircraft inlet because the inlet is part of the airframe rather than the engine itself. Inlet design varies from one aircraft to another depending on performance requirements, flight speed, and mission profile. Air is drawn into the engine through the aircraft inlet and then enters the compressor section. Inside the compressor, the air is compressed and its temperature is increased. This compressed, heated air is then directed into the combustion chamber. In the combustion chamber, fuel is added to the air and ignited. The burning fuel releases energy by heating and expanding the air, creating a high-energy exhaust stream. As this exhaust stream flows through the engine, part of its energy is extracted by the turbine. The turbine uses this energy to drive the compressor, ensuring a continuous flow of compressed air into the combustion chamber. The remaining energy in the exhaust gases is not wasted, but is instead used to generate thrust. The exhaust nozzle plays a critical role in thrust production. Its geometry is carefully designed to accelerate the exhaust gases as they pass through it. As the hot gases expand within the nozzle, their velocity increases significantly, producing the forward propulsion that moves the aircraft. The thrust generated by the engine can be further increased by incorporating an afterburner, also known as reheat, into the engine design. This system injects additional fuel into the exhaust stream downstream of the turbine, where it is ignited to produce extra thrust when required. Jet engines contain many components that rotate at very high speeds around a central shaft. To safely enclose these rotating parts, the engine is built in the shape of a long cylinder. In the computer-generated drawing, a section of the engine has been removed to allow a clear view of the internal components and their arrangement. At the front of the engine, on the left side of the drawing, is the inlet area that guides outside air into the engine. Immediately downstream of the inlet is the compressor section, shown in cyan. The compressor is connected by a shaft, shown in blue, to the turbine section, which is shown in magenta. This shaft transmits mechanical power from the turbine to the compressor. Both the compressor and the turbine are made up of many rows of small airfoil-shaped blades. Some of these rows are attached to the central shaft and rotate at high speed, while other rows remain fixed in place. The rotating rows are known as rotors, and the stationary rows are known as stators. Together, the shaft, compressor, and turbine form what is known as the turbomachinery of the engine. Between the compressor and turbine flow paths lies the combustion section, also called the burner, which is shown in red in the drawing. This is the area where fuel and compressed air are mixed and burned to produce the high-temperature gases that power the engine. After passing through the turbine, the hot exhaust gases flow into the nozzle and exit the engine. The nozzle performs two essential functions. First, it accelerates the hot exhaust gases to produce thrust. Second, it helps control the mass flow rate through the engine. According to the thrust equation, the thrust produced by a jet engine depends on both the change in velocity of the exhaust gases and the mass flow rate passing through the engine. The Pratt & Whitney F100 is an afterburning turbofan engine. In the drawing, the flame holders for the afterburner are shown in orange within the nozzle section. These flame holders stabilize the flame during afterburner operation, allowing additional fuel to burn efficiently and provide a significant increase in thrust when required. In the animated version of this slide, the engine is shown with its main parts separated from each other. This simplified view is intended to help you identify the major sections of the engine and understand their individual roles before seeing how they operate together, as a complete system. The inlet section guides outside air into the engine and delivers it smoothly to the compressor. The compressor section increases the pressure and temperature of the incoming air, preparing it for efficient combustion. Next, the combustion section or burner is where fuel is added to the compressed air and ignited, producing high temperature, high energy gases. Following the combustion section is the turbine, which extracts energy from the hot exhaust gases to drive the compressor through the connecting shaft. Finally, the exhaust nozzle accelerates the remaining exhaust gases and directs them out of the engine to produce thrust. By viewing these parts separately in the animation, it becomes easier to understand the purpose of each section and how they combine to form a working turbojet engine. Turbojet aircraft operate on the principle of accelerating a relatively small mass of air to a very high speed. Thrust is produced by increasing the velocity of the air passing through the engine and ejecting it rearward. Maximum efficiency is achieved when the speed of this accelerated air closely matches the speed of the aircraft. For turbojet engines, this condition occurs at very high flight speeds, which is why turbojets do not reach peak efficiency until aircraft speeds approach Mach 2. At lower, subsonic speeds, turbojet engines are less efficient. Under these conditions, turbofan engines are significantly more efficient and also much quieter. This improvement comes from accelerating a larger mass of air to a lower exhaust speed, which produces the required thrust with less wasted energy and reduced noise. The explanation presented here is an elementary view of the turbojet engine and focuses specifically on what happens to the air as it passes through the engine. Large quantities of surrounding air are continuously drawn into the engine through the inlet. In some regions, such as England, this component is referred to as the intake, which is a more descriptive term because the compressor actively pulls air into the engine. In this example, the inlet is shown as a simple tube-shaped design similar to those found on airliners. In reality, inlets come in many different shapes and sizes, depending on the aircraft's mission, speed range, and operating environment. At the rear of the inlet, the airflow enters the compressor. The inlet's role is to deliver this air to the compressor with minimal turbulence and pressure loss, so the engine can operate efficiently. The compressor consists of many rows of airfoil-shaped blades arranged in stages. Each row produces a small increase in air pressure, and together these stages raise the pressure of the airflow to a level suitable for combustion. In operation, the compressor functions in a manner similar to an electric fan, but instead of moving air for cooling, it compresses the air for combustion. Energy must be supplied to turn the compressor, and this energy comes from the turbine section of the engine. By the time the air exits the compressor, it is at a much higher pressure than the free stream air outside the engine. This high-pressure air is essential for efficient fuel burning and high engine performance. The high-pressure air then enters the burner, or combustion chamber. In this section, a relatively small amount of fuel is mixed with the air and ignited. In a typical jet engine, approximately 100 pounds of air per second are combined with only about 2 pounds of fuel per second. This illustrates that most of the exhaust gas flowing through the engine originates from the surrounding air rather than the fuel itself. The combustion process adds energy to the airflow by increasing its temperature and causing it to expand. The result is a stream of hot, high-energy exhaust gases that flow toward the turbine. As the hot exhaust gases leave the burner, they pass through the turbine section. The turbine operates in a manner similar to a windmill. Instead of requiring energy to turn its blades and create airflow, The turbine extracts energy from the moving gas stream, causing the turbine blades to rotate. In a jet engine, the turbine and compressor are connected by a central shaft. The energy extracted by the turbine is used to drive the compressor, allowing the engine to maintain continuous airflow and combustion. Although the turbine removes some energy from the exhaust gases, the flow leaving the turbine is still at a higher pressure and temperature than the free stream air. After passing through the turbine, the exhaust gases enter the nozzle. The nozzle is shaped to accelerate the flow as it exits the engine. As the exhaust velocity becomes greater than the free stream velocity, thrust is produced in accordance with the thrust equation. For a jet engine, the mass flow rate exiting the engine is nearly equal to the mass flow rate entering the engine, since only a small amount of fuel is added to the airflow. The amount of mass flow through the engine is usually controlled by flow choking at the nozzle throat, which limits the maximum flow rate and helps establish stable engine operation. The role of the nozzle in a turbojet engine. The nozzle of a turbojet engine is usually designed so that the pressure of the exhaust gases at the nozzle exit is brought back to the free stream pressure of the surrounding air. When this condition is met, the pressure difference between the exhaust and the atmosphere does not contribute to thrust. As a result, the pressure area term in the general thrust equation becomes zero, simplifying the thrust calculation for a turbojet engine. When the free stream conditions are identified using a subscript 0 and the exit conditions are identified using a subscript E, the thrust produced by the engine can be expressed in a simplified form. The thrust, denoted by F, is equal to the mass flow rate multiplied by the exhaust velocity at the exit minus the mass flow rate multiplied by the free stream velocity. In equation form, this is written as: the thrust of a turbojet engine is equal to the mass flow rate of air multiplied by its velocity at the engine exit minus the mass flow rate of air multiplied by its velocity at the engine inlet. This equation shows that thrust depends on the change in momentum of the airflow as it passes through the engine. The thrust equation contains two distinct terms. The first term, the mass flow rate of the exhaust air multiplied by its velocity at the engine exit, is commonly referred to by aerodynamicists as the gross thrust. This term represents the momentum of the exhaust gases leaving the nozzle and is largely determined by the conditions within the nozzle, such as exhaust velocity and mass flow rate. The second term, the mass flow rate of the air multiplied by its velocity at the engine inlet, is known as ram drag. This term represents the momentum of the air entering the engine due to the forward motion of the aircraft. Ram drag is primarily associated with inlet conditions and increases as the aircraft speed increases. For clarity, the actual thrust produced by the engine is referred to as the net thrust. According to the thrust equation, net thrust is equal to the gross thrust produced by the exhaust minus the ram drag associated with the incoming airflow. This relationship highlights the importance of both inlet and nozzle performance in determining the overall effectiveness of a turbojet engine. Operation of a turbojet engine. The basic design of a turbojet engine consists of several key components arranged in sequence to produce thrust efficiently. The gas turbine engine includes an air inlet, a compressor stage driven by the high-pressure turbine, a combustion chamber, and high-pressure and low-pressure turbine stages. Compressed air from the compressor is mixed with fuel in the combustion chamber, where it is ignited. The resulting high-temperature gases then flow through the turbine stages, which extract energy to drive the compressor before being expelled through the propelling nozzle. the nozzle accelerates the gases to a high velocity, producing propulsive thrust by increasing the momentum of the flow, which includes both the air and the combustion products. The operation of a turbojet engine can be understood in terms of the Brayton cycle, a thermodynamic cycle that governs gas turbine performance. The operation can be divided into 5 primary stages. 1. Air intake stage. The intake stage is located at the front of the engine, ahead of the compressor. Its main function is to slow down the incoming air, slightly increasing its static pressure. For efficient operation, the airflow entering the compressor must always be subsonic, regardless of the aircraft's airspeed. In supersonic flight, special diverging ducts with doors or baffles are used to reduce the incoming flow to subsonic speeds before it reaches the compressor. 2. Compressor stage. Once the air enters the compressor, it is directed over spinning blades and stationary vanes. Each stage of the compressor produces a small increase in air pressure, and successive stages result in a significantly higher overall pressure. Older turbojet engines used fixed vanes or stators before the moving rotor blades. Modern engines, however, employ stators with variable pitch to direct the airflow onto the compressor blades at optimal angles depending on the engine's speed and flight conditions. The high-pressure turbine drives the compressor via a forward-facing shaft, transferring energy extracted from the hot gases to maintain continuous compression. 3. Combustion stage. After compression, the high-pressure air enters the combustion chamber or combustor, where fuel is injected and ignited. This process raises the temperature of the airflow significantly, producing high-energy gases. Unlike piston engines, where combustion occurs as a rapid increase in pressure in a confined space, combustion in a turbojet is a continuous, nearly constant pressure process. The heated airflow leaving the combustor carries substantial energy into the turbine. 4. Gas generator turbine stage. The gas generator turbine extracts energy from the hot exhaust gases to drive the compressor and maintain the engine cycle. This stage rotates faster than the compressor, adding significant kinetic energy to the airflow. As air is compressed, both its pressure and temperature increase, creating extremely hot gases that must be carefully managed to avoid damaging the turbine blades. Some compressed air is bled downstream of the combustor to reduce the gas temperature before it reaches the turbine blades, protecting them from overheating. The high-pressure and low-pressure turbine blades are constructed from advanced steel alloys capable of withstanding extreme temperatures. Internal cooling passages within the blades ensure that material temperatures remain within safe operating limits. 5. Exhaust stage through the nozzle. Finally, the hot gases pass through the exhaust nozzle, where they expand and accelerate to produce a high-velocity jet. This accelerated flow generates the thrust that propels the aircraft forward. One drawback of this high-speed exhaust is the significant noise it creates, which is a common characteristic of turbojet engines. The design of the nozzle is crucial for converting the energy of the exhaust gases into maximum propulsive force while controlling flow characteristics. Pressure variation through a turbojet engine. To understand how a turbojet engine produces thrust, it is helpful to look at how air pressure changes as it flows through the engine. In the computer-generated illustration, pressure is color-coded. Blue represents the lowest pressure, while white indicates the highest pressure. Air enters the engine through the inlet, located at the left side of the drawing. The inlet directs the incoming air smoothly toward the compressor while ensuring minimal turbulence and pressure loss. Once the air reaches the rear of the inlet, it enters the compressor, which consists of multiple rows of airfoil-shaped blades. Each row of blades increases the air pressure slightly, and as the airflow progresses through successive rows, the pressure rises significantly. By the time the air exits the compressor, it has a much higher pressure than the surrounding free-stream air. The high-pressure air then enters the burner or combustion chamber, where a small amount of fuel is mixed with the air and ignited. Combustion occurs at nearly constant pressure, dramatically increasing the temperature of the airflow and adding energy to the exhaust gases. The hot exhaust then flows into the turbine, which extracts energy from the high-energy gases to drive the compressor via a central shaft. While some pressure is lost during this process, the gas entering the nozzle still has a higher pressure than the free-stream air. Finally, the nozzle converts the remaining high pressure and temperature into high velocity. As the exhaust gases accelerate beyond the free-stream velocity, thrust is generated according to the turbojet thrust equation. This step-by-step variation in pressure from the low-pressure air at the inlet to the high-pressure gases at the compressor exit, and finally to high-speed exhaust, illustrates the fundamental principle behind turbojet propulsion. Engine pressure ratio (EPR). The engine pressure ratio, or EPR, is a key parameter used to describe the performance of a turbojet engine. EPR is defined as the total pressure ratio across the engine, meaning it compares the total pressure at the engine exit to the total pressure at the compressor inlet. Standard station numbering system. In jet engine analysis, it is essential to identify specific locations within the engine so that pressures, temperatures, and other flow properties can be measured, compared, and calculated consistently. This is accomplished using the standard station numbering system, which assigns numbers to key points along the engine's airflow path. Each station represents a reference point where measurements can be made for performance analysis or control purposes. Typically, the numbering system begins at the air intake and progresses toward the exhaust nozzle. The commonly used station points are: Station 0, free stream conditions outside the engine, before the inlet. Station 1, immediately at the entrance to the engine inlet. Station 2, compressor face or the entrance to the compressor. Station 3, exit of the compressor. Station 4, entry into the combustion chamber or burner. Station 5, exit of the turbine or the end of the high energy extraction stage. Station 8, exit of the nozzle where the exhaust gases leave the engine. Some systems include additional numbers for intermediate points, such as Station 6 and Station 7, depending on the complexity of the engine, for example, multi-stage turbines or afterburners. The station numbering system provides a standardized way to describe locations inside the engine, making it easier to discuss performance, calculate pressure ratios, and analyze temperature changes. For example, when calculating engine pressure ratio (EPR), the total pressures at Station 2, compressor face, and Station 8, nozzle exit, are used. By referencing these standard stations, engineers and pilots can accurately measure and compare engine performance across different aircraft and engine designs. This system is widely used in textbooks, technical manuals, and performance charts, and it is essential for understanding engine operation, troubleshooting, and performance monitoring. Using the standard station numbering system, EPR is the ratio of the total pressure at the nozzle exit, PT8, to the total pressure at the compressor face, PT2. One important aspect of EPR is that it can be easily measured on a running engine and displayed directly to the pilot on a cockpit dial. This is why EPR is defined in terms of pressures at engine stations rather than relative to free stream conditions. It is also important to note that total pressure losses in the inlet are not included in the EPR measurement. Despite this, if the EPR, the inlet pressure losses, and the corresponding engine temperature ratio, ETR, are known, the engine thrust can be accurately determined. By combining this information with nozzle performance characteristics and the thrust equation, the actual propulsive force generated by the engine can be calculated. EPR can also be expressed as the product of the pressure ratios across each major component of the engine. Using the station numbering system, this can be written as engine pressure ratio, EPR, is the total pressure at the engine exit divided by the total pressure at the engine inlet. It can be expressed as the product of the pressure ratios across each stage of the engine: low pressure compressor, high pressure compressor combustor, and nozzle. Here. PT3 divided by PT2 is the compressor pressure ratio, representing the increase in pressure as the air passes through the compressor blades. PT4 divided by PT3 is the burner pressure ratio, representing the small pressure change through the combustion chamber. PT5 divided by PT4 is the turbine pressure ratio, representing the pressure drop as energy is extracted by the turbine to drive the compressor. PT8 divided by PT5 is the nozzle pressure ratio, representing the conversion of pressure into high-velocity exhaust flow to produce thrust. This breakdown allows engineers and pilots to understand how each engine component contributes to the overall pressure rise and engine performance. Temperature variation through a turbojet engine. Just as air pressure changes as it flows through a turbojet engine, the temperature of the airflow also varies along the engine. In the computer-generated illustration, temperature is color-coded. Blue represents the lowest temperature, while white represents the highest temperature. Air first enters the engine through the inlet at the left side of the drawing. From there, it moves into the compressor, which consists of multiple rows of airfoil-shaped blades. As the air passes through the compressor, its pressure increases in stages. This increase in pressure is accompanied by a rise in temperature because the compressor does work on the airflow. According to basic physics, when a gas is compressed, its internal energy rises, which leads to an increase in temperature. After compression, the high-pressure air enters the burner or combustion chamber. Here, a small amount of fuel is added and ignited. Combustion occurs at nearly constant pressure, and the energy released significantly heats the airflow. The maximum temperature in the engine is reached within the burner as the fuel-air mixture burns and expands. The hot, high-energy gases then pass through the turbine. As the turbine extracts energy to drive the compressor via the central shaft, the gas loses some of its thermal energy. Consequently, the temperature decreases across the turbine. However, the airflow leaving the turbine still has a higher temperature than the free stream air outside the engine. Finally, the gases pass through the exhaust nozzle, where the remaining high pressure and temperature are converted into high velocity. The acceleration of the gases through the nozzle produces thrust, as described by the thrust equation. By observing the temperature variation throughout the engine, from low temperature at the inlet, rising through the compressor and burner, and decreasing across the turbine, we can better understand the energy transformations that make turbojet propulsion possible. Engine temperature ratio, ETR. The engine temperature ratio, ETR, is a key performance parameter that describes the total temperature change across a turbojet engine. Using the standard station numbering system, ETR is defined as the ratio of the total temperature at the nozzle exit, TT8, to the total temperature at the compressor face, TT2. Like the engine pressure ratio, EPR, ETR can be easily measured on an operating engine and displayed to the pilot on a cockpit instrument. This allows real-time monitoring of engine performance during flight. Knowing the ETR together with the corresponding EPR makes it possible to calculate the engine thrust accurately using the nozzle performance data and the thrust equation. ETR can also be expressed as the product of the temperature ratios across the individual engine components. Using the station numbering system, this can be written as the engine temperature ratio, ETR, is the total temperature at the engine exit divided by the total temperature at the engine inlet. It can be expressed as the product of the temperature ratios across each stage of the engine: low pressure compressor, high pressure compressor combustor, and nozzle. Here, TT3 divided by TT2 is the compressor temperature ratio, representing the temperature rise as air is compressed. TT4 divided by TT3 is the burner temperature ratio, representing the increase in temperature from fuel combustion. TT5 divided by TT4 is the turbine temperature ratio, representing the reduction in temperature as energy is extracted to drive the compressor. TT8 divided by TT5 is the nozzle temperature ratio, representing any additional temperature changes as the exhaust gases accelerate to produce thrust. By breaking ETR down into these component ratios, engineers can analyze how each part of the engine contributes to the overall energy transformation, and pilots can monitor engine health and efficiency during operation. Afterburning in turbojet engines. Military aircraft often require a significant boost in engine thrust for short periods, such as during takeoff, rapid climb, acceleration into supersonic flight, or specific combat maneuvers. This boost is achieved using an afterburner, which is sometimes referred to as reheat. An afterburner works by injecting additional fuel into the hot exhaust stream of the engine and burning it in an extended tailpipe. The principle is straightforward. Introduce and ignite extra fuel in the exhaust to generate large amounts of additional thrust. The afterburner consists of several key components. Fuel spray bars inject the raw fuel into the exhaust flow coming from the engine core. Flame holders stabilize the combustion process, ensuring that the flame continues to burn steadily as it moves down the tailpipe. An adjustable exhaust nozzle is required for afterburner operation, usually with 2 or 3 positions, to manage the increased volume and velocity of exhaust gases safely. The engine's core exhaust contains sufficient excess oxygen to support afterburner combustion, so no additional air inlets are needed. When the afterburner is lit, the resulting exhaust flame is often visually dramatic, partly because the flow speeds are supersonic and the hot gases form diamond-shaped shock waves in the tailpipe. While afterburning can nearly double the engine thrust, it comes with significant drawbacks. The thrust-specific fuel consumption increases substantially, meaning the engine burns fuel at a much higher rate relative to the extra thrust produced. For example, the Pratt & Whitney F100 PW220 used on the F-15 and F-16 consumes approximately 0.76 pounds per hour per unit of thrust without the afterburner and 1.94 pounds per hour with the afterburner. The high-speed exhaust also produces a dramatic increase in engine noise, which is a characteristic feature of afterburning turbojets. In short, afterburners provide a temporary but powerful thrust boost, making them invaluable for military performance applications, but at the cost of significantly higher fuel consumption and noise. Afterburners are commonly used by military fighter aircraft to provide extra thrust during critical flight phases such as takeoff and the initial climb. During these operations, the high noise levels produced by the afterburner are particularly noticeable to observers on the ground due to the supersonic exhaust velocities and intense combustion in the tailpipe. While afterburners are often associated with turbojet engines, they were also used on the Concorde, which employed afterburning turbojets to achieve supersonic cruise speeds. Afterburning is also possible with turbofan engines, especially in military aircraft designed to operate in the transonic and low supersonic speed ranges. In these cases, afterburning allows the engine to temporarily boost thrust for acceleration or combat maneuvers while maintaining reasonable efficiency at lower subsonic speeds. For aircraft operating across a wide range of speeds and flight conditions, a low bypass ratio turbofan is often the preferred design choice. This type of engine provides a balance between subsonic efficiency, supersonic performance, and the ability to use afterburning when necessary. In all cases, matching an engine to a specific aircraft requires careful consideration not only of performance requirements, but also of weight, cost, and installation constraints. Selecting the right engine involves trade-offs between thrust, fuel efficiency, noise, and overall aircraft design to ensure that operational goals are met safely and effectively. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following is not a turbojet engine part? The correct answer is propeller. Question 2. Which of the following is a correct thrust equation? The correct answer is the thrust of a turbojet engine is equal to the mass flow rate of air multiplied by its velocity at the engine exit minus the mass flow rate of air multiplied by its velocity at the engine inlet. Question 3. Which of the following is the correct order of turbojet engine's parts? The correct answer is compressor, combustion chamber, gas turbine, nozzle. Question 4. What do we use to increase the thrust of the turbojet? The correct answer is afterburner. Question 5. How many stages does the Brayton cycle have? The correct answer is 5. Unlock the world of aerospace engineering with my other expertly designed courses. In aerospace engineering, Basics of Aerodynamics, you'll explore how air interacts with moving aircraft and how aerodynamic forces influence performance, giving you a strong foundation in the principles that enable efficient lift, stability, and control in modern flight. Then take your knowledge to new heights with aerospace engineering, aerodynamics, and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about turbofan engines. See you in the next video. Bye.